So we're here today to talk to you about one of our favorite topics, ZFS. So give you a little overview of what ZFS is, what the heck were we thinking anyway, for those of you who haven't had time to look at it much. So one of the biggest concepts we really wanted to introduce in ZFS was the concept of pooled storage. That is, get rid of the notion that a file system is tied to a unit of physical storage, whether it be a disk or a volume or whatever. We wanted it to operate more like what a virtual memory system does for memory. That is, when you want to add more memory to your server, what do? Well, theoretically, you power it down first, plug in more DIMMs, turn it on, poof, you're done. You don't run dim config or create virtual DIMMs or mount them on applications or anything like that. It's just everything gets better. It's all automatic. It's a resource that's managed by the operating system on behalf of applications. Application needs more memory, calls malloc. It's done using it, calls free. That's all there is. And in the meantime, it has a little token, a virtual address that it gives to the operating system to reference the data that it's storing. So why can't storage be the same way? More automatic, less user twiddling, and just let the computers do what they're good at, which is managing resources and doing all the grunt work. So the other thing we really wanted to introduce was we wanted to have things always be consistent. You know, the database guys have been doing this for, well, literally decades and seem to be doing a pretty good job at it. So we really wanted the core of ZFS, the guts in the middle, to be a transactional object system. So everything's always consistent on disk. It doesn't matter what kind of data you're storing in there, whether it's file, block, swap, root, whatever. It's just, at its heart, it's a transactional object. The third thing was we really wanted to make a reliable storage system by having provable end-to-end data integrity. That is, create a signature of the data when the application generates it, and then later, when the application consumes it, validate that it's still the same data. So historically, people have said, you can't do that, making a pass over the data, evil, just don't. However, a lot of things have changed since people last seriously investigated this problem. That is, everything in compute has gotten faster. CPUs are about 1,000 times faster, memory is about 100 times faster, and disk is about 10x faster than it was, say, 10, 15 years ago. So while everything's faster, the ratios of these speeds has changed somewhat dramatically. So what that means is that before, the idea, back in the early 90s of making a pass over data while it streams in from your I/O subsystem and out the network was just, syntax error, can't do that. But now what we found is that making a pass over the data can happen at speeds that are, saturating the memory bus, so multiple gigabytes a second per core. So either you have one heck of an I/O subsystem to keep up with that several gig a second that a single core can validate, or much more likely, use a fraction of a CPU to validate, the hundreds of megs a second that's flowing through your system. And lastly, because people's storage systems are growing ever bigger, people don't say, wow, look, a terabyte disk, great, I just have to buy one for my data center. Nope, people buy more disks and they get ever bigger, and that's a lot of storage to manage. So why not let the computer help you out and provide just simple administration, concisely express your intent, and let the file system and, or ZFS in particular, handle all the details of getting that work done.
But Bill, I thought that storage was a solved problem. Surely all the things that exist in storage today are happy and wonderful. Could you give me examples of what's wrong with storage today?
I can't think of a single thing. Oh, these, yes, that's right. Boy. So some trouble with existing file systems, and they're not listed in any particular order. But number one is that there's really no defense against silent data corruption. Anything that happens to your data anywhere along the path can potentially cause you problems. And people say, well, how often does that really happen anyway? Well, it happens often enough that people notice. So noisy data corruption, which is where you do an I/O to a drive or a storage array, twiddle your thumbs for a while, and it comes back and says, gee, sorry, pal, couldn't get that data for you, and here's why. Everybody in the world knows how to deal with that. Any volume manager, any file system, when the storage subsystem is polite enough to tell you it couldn't do what you asked it to, yeah, easy to deal with. What's very difficult to deal with traditionally is the idea that you give the I/O subsystem a request, and it comes back and says, here's some data, and really wasn't the data you were looking for. That is a lot harder to deal with. And as a person from one of the world's largest drive vendors once told me, is there are two kinds of disks in the world, those that have failed and those that are about to fail. And experience has sort of proven that one out. The second thing is that when you're talking about petabytes of data, how much of your time do you think you're going to spend managing that? Probably far more than you would like. So it's really brutal to manage things of that kind of scale. You got, first of all, you introduce some new storage in there. What's the first thing you got to do? Label the disk, partition it, grind them up into volumes, and provision them. How much is this file system going to need? How much is that file system going to need 2 years from now? I don't know. I just want to have enough storage. And edit your favorite files in the operating system to make sure that they're remembered. And what do you get in return for all this work that you just did? Oh, you get lots of limits, just what you wanted. You can only have so big a file system. Files are limited to a particular size. You only have so many inodes. You only have so many files per directory, things like that, or number of snapshots in some cases. And there's different tools to manage different kinds of data. There's one for managing files, one for managing block storage, one for iSCSI, one for NFS, one for CIFS. What a pain. And then again, most things aren't portable between platforms. I create a file system on x86. I want to take it over to my PowerPC or SparkBox. Yeah, we're sorry about that. Or if it is portable, usually what they do is, like in ext3, they say, everything on disk, little endian. So if you're on a big endian system, hope you like byte swapping. Similarly, like Veritas, it's all big endian. So if you run it on a little endian system, same thing, byte swapping all day. And lastly, because of the way a lot of these were designed, things tend to be slow. Back when you had a 100 meg file system and you're only going to have a few thousand files, linearly scanning a directory to find the entry you want, what's the big deal? Now if you have, as some of our customers do, literally hundreds of millions of files in the same directory because it's really a directory full of hashes, well, now that linear scan is going to cost you a little bit more. And similarly, fine-grained locking, nope, usually not there. You get fixed block sizes, all sorts of painful things that have just grown up historically over time. So what are we really trying to do? Really just trying to end the suffering. Figure out why has storage gotten so complicated? Because people aren't dumb. They do things for a very good reason. But 10 years from now, does that reason still exist? Well, probably not. Computing has taught us one thing, is that change is a rather frighteningly fast and constant thing. So when you actually dig down to what are the fundamental laws of physics in solving this problem, turns out that there are a lot of obsolete assumptions you encounter along the way. So what we decided to do is to design an integrated system from scratch, handling everything from the application down to the storage and back again. Literally start with a screen full of tildes, if VI is your editor, and off you go.
Of course, VI is your editor.
Well, you never know.
So, of course, you've probably heard Andrew Morton famously has called ZFS a rampant layering violation. And we take a somewhat different view, of course, which is that actually the layers that exist in the storage subsystems today are actually part of the problem. And it's useful, though, to go back in time and ask ourselves, why do volumes exist? Why are things structured this way? And if you think about it, going back to the late 80s when this technology started to come into existence, it was all in the same time frame as Patterson's rate paper, and people started to exceed the capacity limits of individual disk drives. And originally, the idea was that there was if you go back even before that, that a disk was, comparatively speaking, a large thing. There was a lot of storage on there. And in fact, the first thing you do with the disk is slice it up into partitions. And then you would have a file system managing each partition. But as people's needs for data grew, they wanted to have the ability to do a number of things. To have either more storage capacity in the form of multiple disks, or redundancy for the data, so you can tolerate drive failure, so Garmin or RAID. And then improve bandwidth in the form of having multiple drives across which the data gets striped. The nice thing is, you can provide all of those capabilities without changing the interface between the file system and the block device. All you do is insert this little shim layer that ended up being called a volume that speaks the block device protocol out the top and the block device protocol out the bottom. And because of that, it inserts compatibly in between any file system and any storage system. And the nice thing about this is it's fairly easy to write one, right? And in fact, you can even picture, if you've never done it before, you can picture in your mind what the code looks like for, say, concatenation of two 1 terabyte drives, right? You want to create a 2 terabyte volume, so the offset comes in. If it's less than a terabyte, you send it to this drive. If it's greater than a terabyte, you subtract 1 terabyte, send it to that drive. That's it. It's a fairly simple thing. So the good news about the file system volume manager architecture is that you didn't have to change the existing software for it to work. The bad thing, though, is that inherent limitations in that interface are really impossible to fix without tearing it up. So by way of analogy, it's useful to think about what is the abstraction that a volume manager provides. Well, really what it's giving you is a virtual disk, right? Because a volume, as I say, speaks the block device protocol out the top. So it looks like a disk drive to every file system that wants to speak to it. And that means that you can plug it under a file system, it's all compatible. But it means that all the hassles that you're accustomed to, partitioning for each file system, growing and shrinking is a manual process, limited bandwidth, you can see in this picture, we've got a file system, volume manager, and say a pair of mirrored drives. And that's great if what you want is completely partitioned access to the data. But if, as is more typical, there are times when, say, the file system on the left is very busy, and these two are not so much. What you'd really like is the ability to have the bandwidth of all those drives available to you, not just the bandwidth of this one pair. Same thing for capacity. You'd like the ability to say, if one file system needs to grow relative to the others, it should have access to that capacity. So the abstraction that we adopted in ZFS in the pooled storage model is much more like what you have in a virtual memory system with the malloc-free model. Right? You don't create applications with a fixed quantity of memory and then administratively manipulate them. You create them with an essentially infinite address space, and then you populate that just on demand. So it's really like a malloc-free abstraction in which the storage pool is like the page pool of the VM system. Each instance of a file system is like an application, and it simply consumes from the storage pool as it needs things. So when you create a file in ZFS, that causes blocks to be allocated from the storage pool. When you remove a file, that causes the blocks to be given back to the storage pool. So the concept of how much free space do you have in a file system doesn't even really make sense anymore. The file system consumes exactly as much space as the data that it represents, no more, no less. Just as an application, you can talk about the size that it's consuming, but you would never ask, how much free memory does Firefox have? Well, I guess 0. But the concept of an application having free memory doesn't make sense. The VM system is fundamentally global to all applications. And this gives you a bunch of nice things. There's no need to manage partitions because you're just taking all the storage and pooling it. The grow and shrink are not, I say automatically here, but it's not even really automatic as much as it's implicit. It's just as you put load in the file system, things come and go. And there is no administrative operation corresponding to that. You clearly have all the bandwidth, you can see from the picture, the basic idea. When you come in with a bunch of writes and they hit the storage pool, we just stripe those dynamically across however many drives you've got available. And since the storage is shared, there are no partitions to manage in terms of there's this much space for one, that much space for another. It's all dynamic.
So looking at the interfaces Jeff was talking about a second ago is the traditional file system volume manager stack, as he mentioned, is the block device interface on top, the block device interface on the bottom, and it's a pretty straightforward, semantically poor, perfectly adequate interface, which is write this block, read this block. Yay, there you go, read and write. And what this means is that, in the early days, loss of power meant loss of on-disk consistency. And people scratched their heads at this for a while and said, well, we'll just clean it up with FSCK. And then they said, well, really I don't like waiting for FSCK, so let's add journaling. So before I write something to disk, let me scribble on a little Post-it note, note to self, I was removing this file. So that if you lose power, then when you come back up, you read this, say, what the heck was, oh yeah, I was, erasing this file. So that way it was sort of a targeted FSCK, I guess you could think of it as. And that's how you maintain on-disk consistency. So the file system's off doing what it's told, doing a whole bunch of reads and writes to what it thinks of as a disk, which is really the volume manager. And the volume manager is like, wonder what's going on. All I see are these reads and writes. I guess I really have no idea, so better just do as I'm told. So, if the volume manager is providing a mirror, write each block to each side to keep the mirrors in sync. You lose power, guess it's time to resync. Which side of the mirror is the right one? I don't know, how about the left one? And all this is synchronous. And of course, just like the file system guys started doing journaling to help with this problem, the volume managers do dirty region logging or use NVRAM or some other thing such that they keep a little bit of state off to the side. So rather than syncing the entire devices back together, they just do the parts that were in flight at the time. But again, sort of a flip a coin sort of thing in terms of which side of the mirror has your data on it. I don't know. Wish I could tell you. So in ZFS, we factored the problem a little bit differently. So, rampant layering violation comments aside, what we decided to do is say the core function, sort of the workhorse of ZFS is what's called the DMU, the data management unit, sort of mentally in our minds at least analogous to the virtual memory or the memory management unit in a CPU. So what the DMU does is it doesn't know what a file is, doesn't know what a directory is. All it knows is that there are objects and transactions on those objects. And it provides that sort of an interface up to what we call the ZPL, or the ZFS POSIX layer. And what the POSIX layer does, it has all your favorite system calls coming in the top, open, close, read, write, rename, unlink, C times, or U times. And it takes those and translates them into transactions on objects so that given a transactional object store, you could imagine writing the ZPL isn't quite the onerous task it might otherwise be. So for example, a rename system call comes in, says rename this file from this directory to that directory. So what the ZPL does is says, aha, I know just how to do this. I'll create a transaction, and as part of this transaction, I want to modify the object representing the source directory to remove a reference to that file. I want to add a reference to the destination directory to add a reference to this file, and I want to update the file's metadata, or what you would think of as an inode, to update the C time on the file to show that it changed the directories, and perhaps the M time on the destination directory as well. And then close this transaction, and now, in a semantically rich way, I've described exactly what it is I'm trying to do. I'm trying to do these updates, which is renaming a file from one directory to another. And the DMU then takes this transaction, bundles it together with any other transactions happen concurrently in time, and bundles them up into a group that, in a fit of creativity, we called a transaction group. And what this does is it describes a whole set of work that moves the file system from one consistent state to the next. And it bundles these up, sends it down to the SPA, which is not a nice, relaxing place to be, but it's the storage pool allocator. And now what the SPA has sitting in its hand is a very semantically rich description of what it is that it needs to do, all the transactional information, and in fact, a complete I/O dependency graph that the DMU provides. It says, before you modify this, you have to modify this other thing and this other thing in order to maintain consistency. So the SPA, unlike the disks or the volume manager, doesn't have to scratch his head and say, I wonder if it'd be okay to reorder these two writes. No, it has the explicit information in hand to know whether that's a legal transformation or not. And then the SPA is what handles all the grunt work, if you will, of dealing with physical storage devices. How to schedule the data, where to allocate it, how to do compression and encryption and checksumming, and all of these things, how to do the RAID algorithms, how to schedule the heads on the disks. All of this is what's handled in the SPA. And because everything is copy on write, because of the way the DMU and the SPA work together, there's no resync if power is lost. We never overwrite live data, so that if something goes wrong, just like in a database, you can sort of roll back to the previous version if you like. And because of this, the SPA has all the information it needs in hand to do a much more optimal job of scheduling and running the disk. So it runs, you know, at very high speeds most of the time.
So the third major point about the architecture of ZFS is that it's designed fundamentally to provide universal storage. That is to say that the data that you put in a storage pool doesn't have to be thought of as POSIX files or as blocks or as any one thing in particular, but rather we have up to 2 to the 48 data sets, and a data set is just a collection of up to 2 to the 48 objects, each of which is up to 2 to the 64 bytes in size. So each data set is just a flat object store that's transactional. Given that object store, you can put various things on top of it. You can put a POSIX file system, you can put PNFS directly on top of that, you can put network protocols on top of your POSIX file system, and you can also just create a sort of degenerate, simplest case of a data set, which is a data set that contains exactly one object, whose contents are interpreted to be the contents of a block device. So given our volume emulation, you can then stick iSCSI on top of that, or just provide access to raw storage. If you're using Open Solaris, you've probably seen that we have root on ZFS now, and we also have swap and dump devices just coming out of the storage pool as well. And you can even do things like putting your good old friend UFS on top of ZFS, which might sound like a strange thing to do, but it actually turned out to be somewhat useful in some of the
Only 2 steps.
It actually turned out to be somewhat useful in some of the testing that we were doing while we were developing some extensions to UFS. So in the early days of ZFS development, UFS was limited to 1 terabyte, and the UFS team wanted to grow that to 16. And of course, the code changes involved were fairly straightforward, but testing was not, because at the time, 16 terabytes of storage was an awful lot. But what we were able to do is say, that's okay. You don't actually need 16 terabytes of real storage. You just need 16 terabytes of emulated storage that's thinly provisioned, which ZFS provides. And then you can put a UFS file system on top of what is nominally a 16 terabyte volume. And it turns out that with compression enabled, you could put a UFS file system on top of a ZFS volume, and it would consume something like, I think, 18 gig. So a couple of Seagate, what was it, Barracuda at the time,
Yeah.
was sufficient to store all of that data. And it actually allowed us to do better testing than we could do with real storage, because you can ask yourself not just, does it work for 16 terabytes, but how about 16 terabytes minus a sector or plus a sector, all those little edge conditions that are difficult to simulate without having drives of exactly those sizes. The other key thing is that all the features that we're going to describe in the rest of this talk, all the key things that ZFS can do, like taking snapshots and creating writable clones, on-the-fly compression, encryption, all the end-to-end data integrity stuff, all of those features are actually implemented at the DMU level of the code, which means, or in the SPA level, which means that anything that you build on top inherits all of those features. So not only can you have compression for a ZFS file system, but if you have, say, a swap device on top of a ZFS volume, if you've got compression enabled for that, then you effectively have a compressed swap device, or another way of looking at it is you have compressed VM. And similarly, if you want your swap to be encrypted, or if you want your iSCSI to be encrypted, that just flows from the way ZFS is architected, from that rampant layering violation. So, how does this all actually work? The first thing is to just, by way of background, every file system is at some level a tree of blocks. There's some well-known place where you start, you descend from there to find everything else. You may have multiple well-known places, but conceptually it's essentially a tree. And if you want to make an update to a file system of a traditional type, let's say I wanted to modify these 2 blocks in UFS. Well, the way that would happen is you would first write this block, and then you would write that block. And the writes might or might not go out in parallel, and they might or might not go out in any particular order. But if, say, I overwrote the contents of this block, and then lost power before writing the contents of that block, I would now have an inconsistent image on disk from the point of view of the application, because it intended to write both of those blocks as one atomic thing, but in fact, it only got the first half of that. So the way you do it in the transactional system is a very simple principle that drives everything, which is never overwrite live data. Because if you're overwriting live data and you lose power, then you've lost data. So what you do instead is you allocate two new blocks, shown here in green, and notice that having written the contents of these blocks, if I were to lose power now, the tree discoverable from the blue root is still intact. I would still follow from the root of the tree down to this indirect block, to this one, and it would point to these blue blocks which have not been modified. So far, everything's good. However, I've got to link these green blocks into the tree, but I can't just overwrite the blue indirect block, because then you'd have the same problem of inconsistency. So you work your way up the tree, all the way up until you get to what we call the uber block, which is the root of the entire storage pool, and that update is atomic. Now there's a couple things to notice about this. One is that when you go from step 3 to step 4, it's fundamentally atomic operation. You're either going to go, if you lose power before writing the uber block, you have the blue tree intact, and if you lose power after writing the uber block, you have the new tree that contains the two new green blocks, which is what you wanted. A couple things to note though. One is it looks like this would be an awfully expensive thing to do, because in the case of a traditional file system, writing these two blocks is just 2 disk IOs. Whereas what I've shown here is 1, 2, 3, 4, 5 disk IOs. And moreover, there's some ordering constraint on those. The thing is, though, that in reality, the tree is not a binary tree like this. It's wider. And what we find is that when pushing out a transaction group in ZFS, you typically have about 1% of your data is metadata. So if you're pushing out, say, 10,000 data blocks, there will be about 100 indirect blocks and then 1 uber block to write out. So in fact, it's the slideware really that inflates the number. In practice, you don't see those kinds of ratios. The other is, you can imagine how expensive this would be if you did this every single time you want to update a file. Because if what you wanted to do is randomly update individual blocks and individual files, then you would actually have to update this whole tree every time you did that. But in fact, the reason we do transaction groups, which Bill alluded to earlier, is simply to take multiple transactions and do the I/O for all of those at the same time. The reason that that's important is because what then happens is that you get many changes at the data level and changes at the metadata level and at the root of the tree effectively collapse into, because if you have multiple modifications, you really only have to write one of those out the disk.
But Jeff, don't I leak blocks when I do this? I don't get it.
Ah, yes. So one thing you would notice going from step 3 to step 4 is that it would certainly appear that the old blue blocks that were on the left side of the tree get leaked when we update to the new green state of the tree. So what's not reflected in this picture, because it simply doesn't fit in something that you can visualize, is that all of the metadata that ZFS has to keep track of which blocks are allocated and which blocks are free is represented in objects that are updated transactionally. So part of the tree of pending changes would be not only these data changes, but also the fact that these green blocks were allocated and the fact that those blue blocks were free. All of those changes are part of that tree of delta as well that gets updated when the new uber block is written. Now there's a bonus to this, which is that taking snapshots becomes almost easy. And I say almost because there's an easy part and there's a hard part. The easy part is that at the end of a transaction group, if you want to take a snapshot, all you have to do is not free the blocks that you count. So keep the old root block, and now you have a live root and a snapshot root, and you've got the blue one points to the old blue tree as it was before this transaction group, and the green one points to the new tree that folds in all the changes that happened as part of the next transaction group. That's the easy part. And in fact, if what you wanted to do is have a file system that never forgot anything, it would be super easy to create, because every transaction group you would simply keep it, and you wouldn't need to keep track of free space at all. But the tricky bit is, how do you know when a block is truly free? Because the thing that makes taking a snapshot so cheap and so efficient in this picture is that it appears like, wow, there's no work to do, right? You just keep track of the old root block. The problem, though, is that, in fact, what's happened when I took this snapshot is that, for example, this blue block down here implicitly now has two references on it. It's referenced by the blue snapshot. It's also referenced by the live tree. Now, that's awkward because if someone comes along later and frees this blue block, how do I know that there are two references on it? Well, one way, of course, would be to go through and put reference counts on every single block, but then that loses for me the benefit of snapshots being constant time. So how do we do that tricky little bit?
I don't know, Jeff. How do we do it?
Well, the way we do it is there's a traditional way of doing this, which is to have, as you might expect, a bitmap per snapshot. So typically a file system will have in it some sort of data structure, either a B tree or a bitmap that keeps track of which blocks are free and which blocks are allocated. And the simplest thing you could possibly do would be to say, well, in my live file system, I've got a certain bitmap of what blocks are active and which are not. And then I can create a bitmap for each snapshot that I've created, and then OR those things together, and that gives me a summary information about saying what blocks are allocated and what blocks are free. But the problem with that approach is that it's really expensive, right? So there's a block allocation bitmap for every snapshot, which means taking a snapshot is not really a constant time operation. It's really O of number of blocks in the file system. Because however big that bitmap is, which is proportional to the number of blocks, you've got that much space overhead and that much time overhead in creating it. And that fundamentally limits the number of snapshots. And one way to think about that would be, just to put it in concrete terms, picture a file system with O, a 4K block size, and say that you wanted to have 32,000 snapshots, okay? Well, 32,000 snapshots implies 32,000 bits, right, describing each block. 32,000 bits is 4,000 bytes, or 4K. So for each 4K of data, you'd have 4K of snapshot bits. So half of your storage would just be bitmaps describing the snapshots. Clearly, that's really not something that's going to scale to any large number. Because you've got O of n create time. Similarly, you have to go through and recompute the bitmaps on delete. And if you want to do an incremental, a comparison of snapshots, fundamentally, it's easy enough to do, right? If you wanted to compare snapshots 2 and 3, you walk along and see where the bits are equal, and then you say, aha, these bits are different. So now I can say, I know that these blocks changed. But it's only giving you a block level delta. It's telling you what blocks physically changed. And you need some prior snapshot to exist to even be able to compute this. And what we do in ZFS is quite different.
Yeah, so in ZFS, we keep track of a little more than just the disk address of where disks are stored, what people usually call block pointers. Is our block pointer, rather than just being a single integer, is actually a data structure. And in this data structure are stored all sorts of interesting things. One of which is what we call the birth time. Well, what is a birth time? Birth time is an integer. And remember before we were talking about how these individual transactions from the application are bundled together in this transaction group? Each transaction group then is the unit that's synced to disk periodically. And each one of these transaction groups has a serial number associated with it that we call the birth time. So for every single block that gets written, we know what transaction group was that block part of the last time it was written, or, in a very rough sense, what was its time or the ordering of these blocks and how they were updated. So in this picture down here, you can see that all the blue blocks, the thing that we started with, say those were born at time 19, or transaction group 19. The things written in green were born at time 25, and the things here in orange were born in time 37. So now it gets sort of very interesting. So how can we, to answer Jeff's previous question, how do we know if a block is free or not? Well, what happens is that when we say, like, we have these 3 snapshots here, when we go to free a block, say like we wanted to free, I don't know, this yellow one here, these three snapshots are actually linked together in an on-disk data structure to show their relationship, saying that they were taken in consecutive order for this particular file system. So what happens is when, say, like you overwrite this block in time, I don't know, 40, what happens is we say, all right, that's great. Now, how do we know if this block is free? What we do is we say, is time 40, which is the current time, greater than, so we're freeing this block effectively. So is time 37 greater or less than the last time a snapshot was taken? So turns out, no, it's not, because these are two snapshots. This is your current version. So 37 is greater than 25, which means that the snapshot taken at 25 fundamentally cannot have a reference to any blocks born in time 37. So as a result, we know we can free the block. So we free it, add it to the free space map so it can be used again later. Say instead that you were overwriting this block, which was born in time 25. Now you make the same exact comparison. Was this time 25 less than or equal to time 25? Why, yes, it is. So fundamentally, we know that that block has an implicit reference due to this snapshot because it was born in 25, and this snapshot represents the state of the world at time 25. So that's the way we avoid needing reference counts. And what happens then is that we can essentially do order one snapshot creates, because there's no bitmaps we have to update, no on-disk data structures containing, reference counts that we have to update. And as a result, snapshots are extremely space efficient and very quick to do. So you can have essentially an unlimited number of them. So creating them is trivial. You just add a record in this chain of snapshots to show that a new one exists. When you want to delete stuff, that comes the more interesting part. Now, how do I know, for example, that if I overwrote this green block here, essentially, if there were no snapshots, I would have freed him. But now I want to go delete this green snapshot. How do I, once again, know that I'm supposed to now free that green block because he was logically overwritten? Now there comes the other part of the trick. Every one of these snapshots has a data structure hanging off of it that we call a dead list. A dead list is nothing more than a list of block pointers. These block pointers are blocks that otherwise would have been freed except that the snapshot was referencing them. So when we overwrite this block, say at time 40, what we do is we say, you know what, this block would have been freed, but this guy is referencing him, so hanging off this snapshot, we say, yep, this block would have been freed, put him on the dead list. So if we ever go and delete this snapshot, we know that this block now should be added to the free map.
And just in case you're wondering this in your mind as you're thinking about this, a block only ever appears on one dead list. So we don't end up in an O of N situation simply because multiple snapshots reference a block, but rather the most recent snapshot that references the block is the one that contains it on the dead list.
Yep. And so then what happens is that deleting a snapshot is very simple. You scream down this dead list, doing freeze for everything on it, poof, you're done. So you have an order of delta, in other words, how many blocks have changed between this snapshot and its immediate successor. You have an O of delta delete and an O of delta incremental. So this O of delta incremental is also an interesting thing. So for example, if we had a, we wanted to send this entire file system, well, that's trivial. You just send every block, you're done. Well, what if we had already sent the green snapshot somewhere else on some other server and is all backed up? And now we want to know, gee, what's changed between now and time 37 and what we last sent over at time 35? Now we get to do what's called a birth time pruned tree walk. So the only thing we have to search for in this block tree are blocks that have changed since time 25. So we start at the top and say, is 37 greater than 25? Yes, it is. Therefore, there must be work to do. Go down the next level. And I'll just do a left-hand depth first search. Time 37 greater than 25? Yes, it is. This block needs to be sent. Go down the left. Is the time 37 greater than time 25? Yes, it is. So now we send this block. Recurse back up. Is time 25 greater than time 25? Why, no, it isn't. So we know that this entire subtree, which is just a block here, doesn't need to be sent, doesn't need to be visited. Go back up. Is 19 greater than 25? No, it's not. So therefore, we know that this entire subtree doesn't have to be traversed, because anytime we modify a block anywhere on this subtree, we have to update its block pointers as well, or the indirect blocks, so that any indirect block is as new as the youngest child underneath it. So we know nothing in this subtree has changed since time, in this case, 19. And therefore, nothing down here needs to be even visited. And now we're back up at the top. So the only blocks we wound up visiting are blocks that are actually part of the delta between time 25 and time 37.
Yeah. The other cool thing about it is that whereas if you're doing a bitmap-based comparison, you end up generating a block-level delta, in other words, a physical delta between the snapshots. What we end up doing over here is we don't actually send the Uber block or the indirect blocks. We only actually send over the wire the modified data blocks. And because we have the structure of the file system in hand, because we're traversing it through its tree structure, we actually send this over not as here's block number 92, but as here is the contents of file foo at offset blah for size 8K or whatever the size happens to be. So we're sending a semantic object delta. It's saying these are the objects that changed, and these are the regions within those objects that changed, which means that you can be sending from one system to a completely different system with a different RAID structure and a different, you name it, on the other end, and still successfully apply those changes. It's really just like rsync in that sense, except that when you're doing rsync, it has to do, it doesn't get the advantage of being able to do the prune traversal, right? If you ever use rsync, what it does, typically, if you have a large amount of data that you're sending from one place to another, is it will spend hours comparing the two trees on the source and destination systems, coming up with the delta that says what changed, right, based on hash signatures of these things. And then it'll spend maybe 5 minutes transmitting what actually changed, because it's typically not that much. So in other words, what happens is when you have large amounts of data that you're maintaining with rsync, the time it takes to send a delta ultimately becomes metadata bound rather than data bound, because there's just so much of it. And it doesn't have the ability to prune traversal through the tree, because it's looking at it as a file system tree. And of course, when you are looking at a tree of, not a tree of blocks, but a tree of files in a directory, you don't have the information that when a file way down at the leaf level changed, that's not reflected in higher level directories. If it were, that would be very handy, because you would know when you could prune the search. And in fact, that's actually what Apple did to implement their first generation of Time Machine, is they made modifications to HFS Plus and their FS events framework that actually do cause change time information to get propagated up the directory tree, so that they know when they can prune something and in effect get a sort of POSIX level version of this concept.
Yep. And the other thing is that you can generate these deltas between any 2 point in times where you took a snapshot. So I can, as I did in my example just a second ago, generate the delta between 37 and 25. I can also generate the delta between 37 and 19 by, instead of comparing to 25 when I'm deciding what to send, compare to 19. So what I'd wind up doing is sending all the blocks that have a birth time strictly greater than 19. So I'd send the orange one here and the green one here, and I'm done. Don't even need to visit here, because I know none of that has changed since time 19.
Yep. And then one last thing that can be kind of handy is that, unlike comparing two snapshots where you actually need two different snapshots to exist, going based on birth time, you can ask what changed since, say, time 22, whether there was a snapshot taken in time 22 or not. You don't have to know. You can just say what has changed between now and any arbitrary point in the past. Yep.
So that's enough fun for objects and transactions and birth times for now. So what about integrity? Well, an interesting thing, you know, if you've been paying attention to drive spec sheets for the last 15, 20 years, is that the number of uncorrectable bit rate that are specified in drive manufacturer sheets have been roughly constant over this entire range of time. And it's mostly due to economics and the fact that those bit rates are what people consider, you know, good enough. People wouldn't pay, you know, 3 times as much for a drive that's, you know, 5 times more reliable. People are seemingly happy with the reliability they have now and just want the cheapest storage. And what the spec sheets tell you is, yeah, on the order of 1 in 10 to the 14th bits for desktop class drives, which sounds like a lot of data, but it's really only about 12 terabytes. Similarly, 1 in every 10 to the 15th bits, they claim enterprise drafts are an order of magnitude more reliable, but really that's only 120 terabytes if it were true. But you know, a bunch of studies have been done on this, and the delta in bit error rates are actually not that big. So what we find is that you get a bad sector every 8 to 20 terabytes of reads in practice, and that doesn't really depend that much on what kind of drive it is you're using. Now the interesting thing is if the bit rates are staying largely constant, what about capacities? What are those doing? Well, they're doubling on some time scale, between 12 and 24 months, depending on what frame of history you tend to look at. And what that means is that you have an exponential growth in capacity going on your disk drives. And as I mentioned before, people don't say, phew, terabyte drive, now I only need one. They actually are deploying more and more drives in their enterprise. So what this means is that with an increasing number of drives per deployment and an exponential growth in data with a constant error rate, is you're seeing a rapid error rate in the number of latent errors sitting around in your data. And these come in two flavors, as I mentioned before, the silent, which are particularly bad, where you ask for data and you get some data, but not necessarily the data you were looking for, and the noisy data errors, which are, of course, easy to deal with. And flash storage, which you know a bunch of you are probably, like us, paying attention to, isn't going to make anything better. It's actually going to make things much worse.
But Bill, this is so much math. You've got some really little numbers times some really big numbers, and maybe you're just lying. Is there any kind of data?
I do that a lot.
Is there any kind of data you could give me from, say, a trusted European international government thing?
Well, there are these guys that make little mini black holes. I trust them a lot. So our pals over at CERN actually had this very concern, what was this, about a year and a half ago, because you know they're doing all the development on the IT side, getting ready for the wealth of data their Large Hadron Collider is creating. And the last thing, of course, they want is, you know, they fire up the LHC and say, guess what? We found the Higgs boson. And, oh, sorry, that was corrupt file contents. You know, we take it back. So they didn't want that to happen. So they actually wrote a very simple application. They call it FS probe. That is rather simple in nature. They generate a fixed data pattern. They write 1 megabyte of it to a file, sleep a second, append a meg, sleep a second, append a meg, and so on until the file gets 1 gig in size. Then they rewind to the beginning. Sorry for the tape terminology. And they read a meg, verify it against the known data pattern, sleep a second, read the next meg, verify it, et cetera. And the reason for all these sleeps is so that they could run this in the background across the several thousand storage servers in their farm. And what they found was rather amazing. After 3 weeks, there were 152 instances of silent data corruption. That is, nothing told them there was an error. The only way they knew it was wrong was because they knew what they had written before. And while that's great for them running this test, you know, it doesn't really work great for an application, because if you know what it is you're expecting to read, well, you really don't need to do the read. So they previously thought everything was fine, and they found out it wasn't. And actually they ran it, last time I talked to them, they had been running it for several months, and they found over 1,600 instances of silent data corruption. And there's no one single cause behind these. There's actually a wealth of causes behind them. But as you would expect, the hardware RAID that saw these noisy data errors did a bang-up job. Is like, oh, bad block, I know exactly what to do, reconstruct it. But when they were silent, nobody thought anything was wrong, no action was taken, bad data got passed to the application. So what this really says is that you really need to have end-to-end verification of your data in order to catch silent corruption. And really what that means is that the same fault domain that you're running your application is, that is typically CPU and memory, the earliest point where the application, you know, generates its data and where it's eventually consumed, is the place fundamentally where you need to authenticate and verify the checksum on this data. Otherwise, if you move it down the I/O stack somewhere, that means that there's then a path between where the application generated and consumed the data and where it's checked and verified that could induce silent data corruptions, and you know, all that was for naught. So, of course, This is something that we think a lot about in ZFS. And we said, hey, let's checksum our data. Of course, we're not the first people in the world to say that. But typically, what you find in a lot of solutions is when you find some amount of data stored right next to some checksum, and the data and checksum go together hand in hand. 520 byte sectors on disk drives are a very popular way of doing this. And some of the bad things about this is any self-consistent block will pass, meaning that as long as the data and the checksum right next to it are the same, well, everything's great. If you have a stray write or a phantom write especially, those are really difficult to detect. And the reason that this exists is because there's really a fundamental layering problem here between the file system and volume manager, where you can't say, hey, I want my data back, and here's what I expect it to taste like, take appropriate action if it's not like that. All you get to say is read. So this data right next to the checksum is great if the kind of failure mode you expect out of a disk drive is what we call bit rot, which is a few bits have flipped, and that's that. But if you look at the way disk drives work today, that failure mode is becoming increasingly uncommon. They're pushing the limits of physics on these drives so hard, I'm sure a bunch of you in this room are actually working on these problems, that they know that just due to physics, there's going to be a certain bit error rate on the media. They have all sorts of ECC or Reed-Solomon algorithms, protecting the data over certain regions that they can then use to correct bits. Some of the newer drives, can handle burst error rates of 320 bits or more. That's a pretty big burst of bad data. So the idea that a couple bits are flipped and the drive didn't notice, becoming increasingly unlikely. However, they actually use this to their advantage. It's not all overhead. There's actually something that comes out of this on the disk drive side, which is most of the time the media is not that bad. There's not 320 bits of bad data just sprinkled everywhere. It actually pretty much works. So they actually use this to their advantage. If you look at the spec sheet for a drive, you see it can do so many IOPS reads, so many random IOPS write, and the numbers are not the same. Usually you can do more reads per second than you can writes a second. And the reason is somewhat interesting. They have all this error correcting data, so what they do is when they seek the armature and they stop it, it doesn't just stop dead. It sits there and wiggles a little bit and settles down. And that settling down takes time, and well, time is performance, so what do? They say, well, media is usually pretty good, and we got all this error correcting data, so why don't we just start reading while the head is still wiggling a little bit? Get some data from one track, get some data from the next, mostly from the track we're interested in, and the error correcting codes will fix it all up. And if it doesn't, no problem, we'll catch it on the next time around, because surely we'll be settled by then. And of course, you can't do the same thing for writes. You actually do have to wait for the head to settle, because scribbling on your neighbor is kind of impolite. So because of that, again, they use these checksums to their advantage on the disk drive, and bit rot is getting to be less and less a problem on spinning Rust. However, the complexity in the firmware that they're pushing these things to, the fact that you can get a disk drive, which is just a miracle of modern technology, for $100 is just mind-blowing, I think. But because of the complexity in these things, you get a whole new class of failure modes. For example, phantom writes, which is where you give the drive a chunk of data and say, please write this to block 72. Drive says, yep, got it, no problem, and just drops it on the floor on its way out. The other thing is what you call a misdirected read or write, which you say, hey, could you give me the contents of block 18, please? It digs around its pocket and says, here's block 18. And ask yourself, gosh, that's pretty frightening. How often can that possibly happen? Well, it happens often enough to give it a name. These are industry standard terms, not something we made up. And also, anyone who's worked in the industry for a while has probably had to debug one of these. And I can tell you from firsthand experience, not a fun way to spend your weekend. So it happens often enough that it's actually a real problem. And furthermore, all of this verification, say if it happens on the storage array, that's great and all, but the data still has a long way to go before your application gets it. Any parity errors, bad lasers on your SAN, any number of things can cause the data to get corrupted from point A to point B.
Bad lasers on your SAN. That's not ever going to happen. I bet you can't cite a single United States government agency that's had that happen.
Well, Center for Disease Control. Yeah, so our friends at the Centers for Disease Control had exactly that happen. They had a little laser on their fiber channel bursting bad data on the SAN that exceeded the ability of fiber channel to detect, much less correct. They had a nice shiny EMC box that was dutifully storing the data, and Oracle and Veritas up running on their server. And of course, they asked for the data back eventually. And the EMC says, well, this is what I got. Still perfect, just like I received it. But of course, it wasn't what the application had written, so Oracle goes off into bad, unhappy land. And they spent a while debugging it, and finally were able to track it down to a bad laser on one of their fiber channel ports, and that's kind of frightening. The other thing is, driver bugs, accidental override, any number of things can happen that seem legitimate from the storage array's point of view, but really aren't legitimate in reality. So in ZFS, we do what the spooks have been telling us to do for, I don't know, about 100 years now, which is in order to validate a message, the best way is to send the message and its validation over separate channels, or at least separate messages. And that's exactly what we do in ZFS. I mentioned before that block pointers are a data structure, and it has the birth time in there as well as the disk address, and it also has this handy-dandy checksum. So as soon as we know where on disk this block is located, we know what it should taste like when it comes back, because we have its checksum. So this will actually catch, not only bit rot, of course, because a few bits are flipped. Checksum, of course, is designed to catch that, but also phantom writes, which are notoriously hard to detect. That is, in this model, if I were to write this data, if I were to say overwrite this data and give it a new checksum, and that just got thrown out the door somewhere, well, the old data matches the old checksum, and you're good to go. But not really. The other thing, whereas in this situation, the old data isn't going to match the new checksum, so that's something you can detect and take action upon. Same thing for a misdirected read. I ask for this block, I get that one instead, data matches the checksum, oh, seems good. Or if you store the location and checksum in there, then you have a weaker checksum, but at least you'll be able to detect misdirected reads in that case. Whereas here, same sort of thing will happen. I ask for this block, get this one instead. This data doesn't match that checksum. Once again, I detect it. And because I'm doing all of these validations of checksums up in server memory, the same place that applications are consuming the data, I'm able to take action on anything that may happen on the way to the theater tonight. And that's great, you say, but how do I know I can trust that checksum? Well, this indirect block is data 2, and it was validated by that checksum, and so on and so forth up the tree. This is what our friends in the crypto business call a self-validating Merkle tree, meaning that the checksum at the root of the tree in the Uber block is sort of like a digital signature for all active blocks in the storage pool. So anything, anywhere in the tree that's corrupted has to pass all these checksums, or we detect the corruption and take action on it.
Well, I certainly appreciate you detecting the problem, but what are you going to do about it?
I'll tell you what I'm going to do. So first of all, let's see what we don't do. This is a more traditional approach. So you have some application connected to some file system, connected to, I don't know, some mirroring volume manager, who's trying it best it can to maintain 2 copies of the same data on 2 different disks. Well, time goes on. You get, misdirected reads, phantom writes, bit rot, any number of things, all stylishly represented by this yellow lightning bolt that turn what would normally be a happy green block into an angry little red block. Time goes on. The application says, hey, I want my data back. File system says, yeah, no problem. I know where I put that. And
Yeah, I got your data right here.
Exactly. Ask the volume manager, and the volume manager is like, oh, cool, I got a mirror. I can choose left or right today. Today is the left kind of day. Let's read it off the left. Reads this, angry red block, no error reported by the drive in the case of a silent data corruption, and it's like, guess it's good data. Dodge the bullet on that one. Passes it up to the file system. The file system is good data. I love nothing more. And if it's file system metadata, off the file system goes in the weeds, freeing free frag or whatever your favorite error message is. And who knows what happens. Or worse yet, it passes it up to the application, who goes off in the weeds doing who knows what on this bad data. And of course, the frustrating part about this, if it ever actually happens to you, is that over here on the other side of the mirror actually was a good copy of the data. And if only you had chosen wisely, things would be much better. So in ZFS, of course, the same thing can happen. Stylish yellow lightning bolts happen to us too. And applications, as they tend to do, eventually ask for their data back. We know where we put it, just like any other file system does, and we do a read off the mirror. Of course, the first thing we do is we say, that's great that the read succeeded, but let me validate that against a checksum. We look at it and say, hey, you're not that happy green block I was looking for. You're that angry red block everyone's been talking about. Throw it out the window. And because we incorporate that rampant layering violation, we know that it's actually a mirror, and there's another potential location we can get the data from, which is the right side. So we read that and we say, all right, it's great that that succeeded. Still need to validate the checksum. As Reagan says, trust but verify. And that actually is good data. So now we can pass known good data to the application, and better yet, go and fix up that angry red block we encountered earlier. And that way, we're back to 2 copies of known good data. No guesswork involved. It all just happens to work. The same principles also apply, as we'll get into later, RAID 5-like scenarios, or RAID 6, whatever your favorite is.
Yeah, and just to give you a sense of how resilient that actually is, and this is my last comment, and then we're going to break for lunch, and we'll resume at 1 p.m. To give you a sense of how resilient this is, one of the tests that we do is to set up a mirrored storage pool, and then bring over a copy of the Open Solaris code, kick off a nice parallel build, and then while that's going on, just scribble random garbage all over one of the drives while the build's going. And invariably, the checksums catch all of it, the thing runs to completion, and you'll see, if you look at the I/O statistics, that there's these thousands of checksum errors going by, but they're all detected, corrected, and you get valid data, despite the fact that you've got this enormous corruption injection rate.